So in this video, I want to do another example where we calculate the volume of a solid of revolution using cylindrical shells. However, this time what I want to do is rotate around the x-axis. And I think because as I mentioned in the last video with cylindrical shells, we'll always either rotate around the y-axis or the x-axis, this video might be sufficient to finish up this section. So I'll go through it a little bit more slowly because I plan on making this the last example of the section. The example that I chose to illustrate this is one we've seen before, where we start out with a region bounded by y equals the square root of x and y equals 1/10 x. We saw this back in 6.2 when we were dealing with washers and shells. The only difference there is back when we saw it in 6.2, we cut it off at x equals 4. We just looked at this region right here. Whereas in this example, I'm not going to cut it off. I'm going to look at this entire region rotated around the x-axis. So the first thing to know is because we're rotating around the x-axis and using cylindrical shells, our variable of integration will be y. And maybe later when I draw the picture, we can make some sense of why it has to be the variable y. But before we even do that, we can kind of start to set up our integral. So we're going to integrate and it's going to be with respect to y. So I'm interested in the y coordinates of the bounds of this region. So this point right here has a y coordinate of 0, and this point right here, we're not thinking about its x coordinate of 100, but instead its y coordinate of 10. So I'm going to be integrating from 0 to 10 with respect to y. If those points weren't given on the graph, we could get them by just setting the two equations equal to each other to figure out the 2 points of intersection. If we want to know the x coordinate of their points of intersection, we would want them both solved for y and then set them equal to each other. So 1/10 x equals the square root of x. But we don't want the x coordinate of their points of intersection. We want the y coordinate of their points of intersection. So what we would have to do before we set them equal to each other is first solve each equation for x. So for this first one, that's easy enough. I just multiply both sides of the equation by 10 to get x is equal to 10y. And for the second one, I'd have to square both sides of the equation to get x is equal to y squared. And now that I have them both written in terms of x, I can set them equal to each other and get 10y equals y squared. And now I have an equation only involving numbers and y's. So if I solve this thing for y, I'll get the y coordinate of the 2 points of intersection. To solve this guy, subtract 10y from both sides of the equation, set it equal to 0 so that you can factor it, and then factor out a y, and you're left with y minus 10 equals 0. So either y equals 0 or y minus 10 equals 0, in which case y equals 10. So just like the picture suggests, the 2 points of intersection are at a y coordinate of 0 and a y coordinate of 10. Those are going to be my bounds of integration. All that's left to do now is to figure out what's inside the integrand here, and then to integrate this thing, find the antiderivative. The harder of those two things will be figuring out what you write right here. It might help if you have this idea that the volume of a shell when we're using the cylindrical shells method is always 2 times pi times r, the radius of the shell, times h, the height of the shell, times the thickness. And the thickness will just be the dy, so really where we're going to focus our attention is the 2 pi r and the h. And the last video talked a little bit about where those come from, 2 pi r being the circumference of a circle, which when I unroll it turns into kind of the base of a rectangle, and the height of that rectangle is just h, which is the same as the height of the cylinder. I don't want to get too much into the theory here. What I want to do is just take this problem more from the student perspective where you're just trying to solve it and figure out what the answer is. So the 2 and the pi are just constants. Really all I need to know is what is playing the role of the r and what is playing the role of h. And I think to figure that out, it might help to arbitrarily pick some y value. It doesn't matter which one, any y value in between 0 and 10. Because kind of informally what this means is we're going to be taking all of the different y values from 0 to 10 and adding up these various expressions that we'll get. So just pick any y you want. I'll pick this one, and then maybe we can think about the shell that would result with that y value. As you're well aware at this point, I'm not much of an artist, but maybe having this little picture here helps you out a little bit. Here, unlike in the previous example, our cylindrical shell is kind of sideways as opposed from being up on end. This is rotated 90 degrees from what we saw in the last example where we were rotating around the y-axis and therefore integrating with respect to x. But just like in that previous example, it's 2 things we want, the radius and the height. The radius is a little bit easier. The radius in my picture is just the distance from here to here. Well, that distance is the exact same as the y coordinate. So playing the role of the r will just be the letter y. The height is the one that's going to be a little bit trickier, this h here. But if you just think about the height of this cylinder, well, it's the distance from here to here. Right, but how am I going to represent that in terms of x's and y's and stuff? Well, the way to think about it is the endpoints of this line segment, this dot right here and this dot right here, both lie on these curves. This endpoint lies on this blue curve. This endpoint lies on this green linear curve, if you want. So I have lots of information about these two endpoints. The information that I really want to know is what are their x coordinates, because the height is just the distance along the x-axis from here to here. So if I had a way to represent how far this point was from my y-axis, in other words, the x-coordinate of this point, and I had a way to represent how far this point was from my y-axis, again, the x-coordinate of this point, I could just take this whole distance and subtract this distance, and I'd be left with this distance, which would be exactly the height. The good news is we have all that stuff. We want to know the x-coordinate of this green line right here. All I got to do is solve this equation for x. Oh, I already did that. How convenient. I want to know the x-coordinate of this point, which lies on this blue curve. All I got to do is solve this equation for x. I've already done that as well. Note that in this bounded region, this x-coordinate is always greater than this x-coordinate. This curve is always to the right of this curve here. So when I talk about the height, I want to take the expression that represents the line minus the expression that represents the curve. What I'm saying is that h is just 10y minus y squared. I can tell you from experience, because this isn't my first time teaching this class, a lot of students will mess that up. A lot of students will understand that the height is just the difference in the two curves. That part's not too bad. And some of them will write 1/10 x minus the square root of x or something like that. But then they'll quickly realize, wait, that can't possibly be right, because then I'd have x's floating around in here and my variable of integration is supposed to be y. So they'll quickly realize they're supposed to solve for x and use these two expressions. But some people will write y squared minus 10y instead of 10y minus y squared. The reason you want 10y minus y squared is, again, because this line is further to the right of this curve. But I can say that as many times as I want. That doesn't mean people aren't going to mess it up. The good news is if you mess that up, it won't completely screw things up. All that will happen is your height will really be the negative of your height. And what that'll end up doing to your answer is it'll tell you that the volume is a negative number, which doesn't make sense. We can't have a negative volume. The good news is that the absolute value of that negative number that you get for the volume will be the correct answer. So if you work through all of these and you figure out that the answer is, I don't know, negative 25, you're like, oh, that can't possibly be right because my volume should be a positive number. You go back and look at it and you're like, oh man, I did y squared minus 10y. I got those backwards. I guess I have to start the whole problem over again. No, you don't. Maybe just write a little note and be like, oh, whoops, this should have been 10y minus y squared, not the other way around. So therefore my answer should be 25, not negative 25. At any rate, before I finish the problem, I should probably integrate this guy. I'd take the 2 pi since that's a constant and pull it out in front. And maybe I could take the y and distribute it through the parentheses. And now the integrand isn't too scary looking. I just need a couple of antiderivatives. The antiderivative of 10y squared is 10/3 y cubed. And the antiderivative of y to the 3rd power is 1/4 of y to the 4th power. And that needs to be integrated from 0 to... Nice thing about tens, 10 cubed is easy to figure out. It's 1,000 times another 10, that's 10,000. So I get 10,000 thirds over here. And 10 to the 4th is 10,000, so I get negative 10,000 fourths over here. And then you don't have to, but I always find myself doing it anyways. I don't do this when I do this on my own, but to illustrate for students, if you plugged in zeros, you'd get a 0 minus 0, so I wrote that over here. This subtraction works out pretty nicely. Let's see, this is 40,000 twelfths, and this is 30,000 twelfths. So 40,000 minus 30,000 would give me 10,000 twelfths, which I guess if I wanted to, I could cancel this 2 with one of the 2's in a 12 to make this 10,000 pi over 6. But I could also cancel the 2 in the 6 with 10,000. And I think what happens is I get 5,000 pi over 3. And that would be my final answer. The key things I want to point out here is these problems, there's really only 2 different types of them. Are you going to be rotating around the y-axis or are you going to be rotating around the x-axis? We're not worrying about the case where you rotate around a line like y equals 2 or x equals 3 or something. It'll always be around the axis. So all your work will come down to is figuring out your variable of integration, figuring out your bounds of integration, and then knowing that the integrand is always 2 times pi times the radius times the height. The 2 and the pi are just 2 and pi, they're constants. The r will always be your variable of integration, so it's either y or in the previous example it was x. And then the height is the only one that's tricky, but the height will always be given by the equation of your curve or curves. In this example, I had to subtract the 2 curves to get the height. You might be like, well, you didn't do that in the last example. Well, I kind of did. It's just that my 2 curves were this equation and y equals 0, my x-axis. So when I subtracted this one, there really wasn't anything to show. But the height is always the top curve minus the bottom curve if you're integrating with respect to x, or the rightmost curve minus the leftmost curve if you're integrating with respect to y. One last thing to be careful of on these, make sure you throw parentheses around here, otherwise the 2 times the pi times the radius will only hit the first of your 2 curves that determine the height, not both of them. Oh, and one last thing, if you're integrating with respect to y, you're going to want to write all your curves in terms of y. In other words, you're going to want to solve them for x. You solve them for x both to figure out the bounds of integration and also to have the equations that you'll plug in for the heights. I think that that's all I got on cylindrical shells, so maybe we'll end this section here.